Hello and welcome once again for another ES340 video. This is going to be the Day 5 Part B video. So I'm going to start by discussing now liquid states. This is carrying on from the previous video where we discussed the diagrams and the various regions where you had something called a compressed liquid. And we should explain what I mean by compressed liquid here in a moment. We also had superheated vapor region and the mixture region, right? So let's actually discuss what I mean by each of those things. So compressed liquid, in this book at least, compressed liquid, liquid and supercooled liquid are all going to be used interchangeably. And the basic idea here is that we say compressed liquid because the pressure tends to be greater than the saturation pressure, or the temperature is less than the saturation temperature, hence the word subcooled liquid. Okay, so we can think of this is why we can think of using these terms interchangeably. So if the temperature is low enough that it's beneath the saturation temperature, then we're in the subcooled liquid or the compressed liquid regime. Or if the pressure is higher than the saturation pressure, again, we're in the compressed liquid regime. Okay, so then we also have the two-phase liquid vapor mixture. So that was that middle part of that plot that we showed last time, the PV plot or the TV plot, either of those two. But in this case, in that central region, we have a mixture of both liquid and vapor. No solid in that case. At the triple point, you can have a mixture of all three, but we're not going to, most of the time, we're not going to deal with the triple point. And the idea here is we can actually express how much of liquid / vapor we have, and the way to do this is using the quality. So the quality, which is given by X, is equal to the mass of the vapor divided by the mass of the liquid plus the mass of the vapor, which is the total mass, right? This is the mass of the vapor divided by the total mass, if you want, or just M. Okay, and because obviously there's no mass in any other states, right? Because it's a two-phase, it's not a three-phase or something like that. So that's the total mass there. So basically the idea is if we, this quantity gets closer to 1 as the mass of the, as we get less and less mass of a liquid, right? And then eventually, actually, if we got all the way over and we were touching the curve on the right-hand side, we would get to the saturated vapor, which would have a 100% quality. So the quality is, I want to make clear that the quality is only useful when we're in the mixture. Okay. It doesn't make sense to then think about the quality as you increase beyond into the superheated region, which we'll talk about in a moment. Obviously, on the other end, you could get to the saturated liquid state by having zero mass of vapor, right? So that would give you a quality of 0. So the quality goes from between 0 and 1, and the closer it is to 1, obviously the closer to the right-hand side of that curve we are. So remember, the curve looks something like this. We had a curve in both cases, doesn't matter which one we're plotting. Like the PV plot, we had a curve that looks something like this. And if we get over here, then the quality is near 1, and over here the quality is near 0. Okay? The quality will be useful for other things as well. For instance, when we need to get values off of tables, which I'll discuss in a moment. So then we also have vapor states, of course. When we get over onto, recall that when we get over to the right-hand side of that curve, so when the quality is, let's say when it hits 1, when the quality hits 1, we're in the saturated vapor. But then if you were to imagine a case where it got above 1, which obviously makes no sense, but as we go over further, the volume gets larger beyond the saturated vapor state. In that region, now we are in the superheated vapor region. So there are cases that we can have superheated vapor as well, just like the compressed liquid. So in this case, we have scenarios like the temperature is greater than the saturation temperature. And you can also see just from this plot that the volume here, the specific volume, this is specific volume, must be greater than the specific volume of the saturated vapor. Okay, so you can have these kinds of scenarios, obviously, as you get further and further over to the right-hand side there. So these are different ways that we can figure out what region we should be in on the plot. Now you can, when we start talking about the tables, which I keep wanting to jump into here, when we start getting into the discussion of the tables, you can start off, say using the saturation tables, but you would quickly figure out, the pressure that I'm dealing with in this scenario is, say, if we go back up here, is greater than the saturation pressure. So that means I should be looking at the compressed table, not the saturated table, right? So I would then switch over to the compressed table. Same with if the temperature was less than the saturation temperature, again, I would switch over to that compressed table. Similarly, we can do things with superheated. So we know, again, if you start at the saturation table and you find out that the temperature you're dealing with is actually greater than the saturation temperature, then you have to jump over to the superheated. I should have written that here. Ooh. I'm going to make that a little better. Okay, so both of those cases get us to the superheated vapor. Okay, since we're talking about these different states, we have mixtures, we have vapor, we have liquid. We're not going to deal a lot with solid, but I will mention that in a moment. But we're not going to deal a ton with it. So we have these different types of transitions, basically. So we have vaporization, which means going from a liquid to vapor. Condensation, which is going from vapor to liquid. We have, of course, melting, which is going from solid to liquid. And we have sublimation, which is going from, this one is actually going directly from solid to vapor directly. So, and obviously, freezing, I should mention. Liquid to solid. Okay, so sublimation and freezing and melting, we're not going to deal a ton with these kinds of things because we're really going to be focused on vaporization and condensation where for most of the things in this course. But of course it is good to know about these other kinds of changes that can happen in the states. Now I will mention just very briefly that there is actually a software called Interactive Thermodynamics, which you can use to look up values of these tables and things like that. I tried at some point to actually download it, and I found that the most recent version wouldn't work for me, so I was worried that, of course, it also wouldn't work for the students, for you folks. So I decided not to use that software, but I'm not going to penalize anybody if they're able to actually get the software and make it work. So it might make looking up values faster off of tables and things like that. Okay, so the tables. Now this is going to be the important part here. So this is going to come back to you over and over again. You probably at some point, in chemistry or whatnot, have learned about the ideal gas law. Well, the ideal gas law makes assumptions about the gas, right? That it has, that it's not too dense and things like this. There's no interactions, all these kinds of assumptions. And the ideal gas law only works well in certain scenarios, right? Because of those assumptions. So the tables are going to allow us to go beyond the ideal gas law because these are actually measured values. And so this is why the tables are going to end up being important. They're going to allow us to figure out things like how much energy how much the energy is changed by going from this state to this state, for instance, and things like that, without having to invoke the ideal gas law, which makes all of those troublesome assumptions that might not be valid in our particular scenario. Okay, so there will be cases where the ideal gas law is just a bad idea to use. And we'll see that the tables are the best thing, obviously, because they're measured values. So, obviously the tables are going to have some importance to us. Now, the problem with the tables is that they can't list every possible value of everything, so they have to obviously pick special cases, like the pressure is equal to 10 bars and things like that, and then the next one maybe is 12 bars, something along those lines. And so then the question becomes, of course, what happens if the value that I'm trying to get is in between those values? So that's where we're going to use linear interpolation. Now, the idea for the linear interpolation is really simple. It goes as follows. Note that we have this, this is called point slope form for a line. This is the point slope form of a line, right, where m is the slope, and x naught and y naught would be a point. And the idea is really simple, that I can just rewrite this as y minus y naught over x minus x naught is equal to m, which is obviously true. We know that that is the case. But as we'll see in a moment, or as I'll show some examples of doing this linear interpolation in the videos, in the example videos, But the idea is really to use this formulation, to our advantage. But typically, obviously, the independent variable that we'll be looking for is not y, but it might be something else, like, as an example, the specific volume. So instead of y, I might have v minus v naught over t minus t naught, but I might actually know is equal to m. Okay, but I might actually know, say, this might be equal to the slope. We might have, might be, say, vf minus vg over tf minus tg, or something like that. Okay, where these are the values, respectively, that are found on the tables at, say, fluid and gas. That's what F and G are going to stand for here. So in your tables, as you'll, I'm going to show an example of a table in one moment, but you just basically set these things equal to each other, and then you can find V using this formulation, which is really fantastic. And, you know, this V naught might be, say, let's say VF, and this T naught might be TF, or something like that. Okay, so, well, actually, this is going to be TG. So let's do it this way. No, T, yeah, sorry, I had it right the first time here. So it might be like T, like this, where T is the value that you know, and you're trying to find V. So you're given T, it's somewhere in between these two values in the table, the TF and the TG. So obviously you can't directly read it off the table. Then you can read these values off the table, the VF and the VG, but you can't obviously just get this V here, so you have to solve for it. So this is an example, and like I said, I'm going to make this all very clear by giving some example problems so that you can see how it's done. But I just wanted to lay out the simple process here that we'll be dealing with. Okay, so that's the basic idea for vapor and liquid tables. Now for saturation tables, so in this case, you know, this process might not, this process could be generalized to other scenarios. It doesn't have to, it doesn't end up having to only deal with that specific scenario. For the saturation tables, what we're going to be interested in is we're either going to have something that's in the saturated state or in a mixture, as we noted before. And the basic idea here is that we can use the quality. Remember the quality that we had up here, which was M vapor over M liquid plus M vapor, right? So we had this as our quality. Now, if we take the specific volume, recall that the specific volume is equal to the volume over the mass. So this is specific volume. This is the volume. Of course, that's the mass. So we can use this to our advantage here. By noting things like if I'm in the liquid state, what I'm going to have, or if I take the total specific volume, because let's say I'm in a mixture, the total specific volume, well, that has to be V in the liquid state, the volume in the liquid state, over M, plus the volume in the vapor state over m. And this is going to work for other quantities that are specific as well. This is why it's going to be useful to get familiarized with specific quantities. That's going to be equal to my v. So v then can be rewritten as the mass of the liquid over the mass times the volume of the liquid, or Vf, plus, where this is the specific volume of in the liquid phase, plus the mass of the vapor over m times the volume of the specific volume in the vapor phase. Okay, and then we can note that what this ends up implying is that we get something like this: 1 minus the specific volume, the quality, excuse me, times the volume of the liquid phase, the specific volume of the liquid phase, plus the quality times the specific volume in the vapor phase is equal to this. Or we can also set this equal to this. And that's going to give us a nice, easy way to do that interpolation in the case where we have a mixture. Okay, so we do have to be careful. This is going to work for mixtures, not in general. So when we do when we deal with those kinds of scenarios, we can use this, but when it's not a mixture, then we have to directly use linear interpolation. Okay, so that's going to be the key part of our a key part of this course. Okay, so now let's actually look at a table so we can get an idea. I mentioned all of these things, and probably not so easy to visualize what I'm talking about. What is it that he's talking about? So let's actually look at a kind of example of this. You can imagine that, let's say that look at the saturation temperature here. So this is actually a superheated table for water. So imagine that I was given that, P equal to 8 bar, or something along those lines, and T is equal to 47 degrees Celsius, right? Well, golly whiz, I'm at P is equal to 8 bar, so I'm pretty good there. But notice that I have temperatures at 40 and 50, but not 47. So how do I find, say, the specific volume? You would use interpolation here. Okay, so this is an example. So I want to find the specific volume in this case, and I would have to then interpolate between these values. So I know it's going to come out somewhere between 0.02846 and 0.02691, somewhere in there, but I have to use linear interpolation to find that value, which I'll show in the next videos. Hope that was quite helpful. See you again next time.